My name is Lalith and I work at the University Earthquake Research Institute at the University of Tokyo. And today's talk is about agent-based simulation for earthquake disaster mitigation. And last couple of days I had the opportunity to talk with some of you, and interestingly, some of you raised these questions. What are you working on? That's one of the common questions. And then some ask, why do you work on economic simulation if you are working at Earthquake Research Institute? So actually these questions are really interesting. So let me first spend 4 slides to answer these questions. Our group at Earthquake Research Institute is mainly interested in large-scale physics-based simulation of earthquake disasters. The motivation for this large-scale, high-resolution earthquake disaster is the making more reliable forecast predictions of the disasters due to upcoming earthquakes. Actually, as you understand, these reliable disaster predictions is very important for policy planning. And when it comes to earthquakes, these are not frequent. They happen once in large earthquakes are happening once in 50 years. So previous big earthquake in Tokyo was 1923. It has been almost 100 years. And current predictions, disaster predictions are based on the historical data. They look at historical data and look at which region has how much what was the peak ground acceleration or peak ground velocity and how much damages were observed. And they make this curve according to those observations called fragility curve and use this to predict what would happen due to next earthquake. And as I mentioned, the earthquakes are not frequent. They are happening once in 50 years or so. And within these 50 years, we advance significantly. Our construction material advances, our design code advances, and our social system advances, and that makes all our past observation useless. And so we need a better approach. And right now, when it comes to the construction, we heavily depend on numerical softwares. They are quite advanced now and can predict behaviors quite accurately when it comes to steel, concrete, and these buildings. So if we can rely on advanced software for construction, why don't you use the same thing for forecasting disasters? But for construction, we have to analyze a single building. Well, we spend significant time and then analyze and then design. But for disasters, we have to simulate the entire city. That's several million buildings in each simulation, and then we have to do many simulations. There are many uncertainties. So we need a dedicated software. But interestingly, in this when we do such a large-scale simulation, we can include up-to-date information of each building, each infrastructure, what's their age, what's their current damage state, and also we can consider all the seismic scenarios seismologists are expecting and calculate what's the probability of a certain building being damaged. And also, not only that, we can include complex interaction of economic entities and buildings and use this to calculate what would happen after a disaster, what would happen to our economy, how did it proceed. So this is our group's interest. Basically, we want to simulate fault rupture. This is one of the simulation we recently I did with one of my students. It's around not very large compared to the larger scale we are talking here. It's around 8 billion degree of freedom. And this is a reproduction of 2018 Palu Koro fault's super shear event. It's a special type of earthquake, as you know. We can see a McCone-like super shear the seismic wave. And this is a simulation done by my colleagues, Professor Ichimura and Professor Fujita. This was a quite old one, actually more than 10 years ago. this involves 40 billion degrees of freedom. Right now, they are doing trillion degree of freedom system, use entire Fugaku. Okay. And in this simulation, I'm sorry, it's a quite old one, 3.5 part of central Tokyo is modeled. So there are 4 soil layers. I will skip the details. I will show only the major part, sorry. And so it involves around 40 billion degrees of freedom. And they model the domain using tetrahedral elements. Sorry. And this yesterday, the day before yesterday, you were taught in the class that the domain has to be decomposed. Each part has to be given to each CPU. And this is, in this video, the slide, it shows that that entire domain is split into nearly 83,000 pieces. This is a single piece. And each is assigned to one computing node and then communicating using MPI and other the shared memory approaches. So they simulate it as a single domain. As we can see, some areas suffer larger deformation, just like light waves, seismic waves interfere, reflect, refract, and at some areas that creates these interactions create a larger deformation. Likewise, we can simulate larger areas with the more powerful supercomputers and calculate, due to different earthquakes, what would be the ground deformation. And on top of that, after that, we can put the buildings on it and then simulate their seismic response. And in this one, next video, we have around 600,000 buildings. And we don't simulate the ground motion. Instead, we input Kobe earthquake seismic motion to each building. And this allows us to do even city scale, large number of simulation of large number of buildings. So basically what we are trying to do is trying to simulate physics involved phenomena from fault rupture to disaster in high resolution, expecting that this will contribute to more reliable seismic disaster assessment. But looking at the entire picture, actually, this is only a part of the problem. This is important because it affects the society and the economy. So if we only focus on this part, we only analyze half of the problem. And one of our project evaluation committee suggested, yes, you are producing very good results in a very high resolution, but there are no tools in the social domain to use this high resolution data and fully utilize and contribute something to the society. And they advise us to work on this one too. And since then, we are working on these tools. And that is why I happen to work on the economy. Now, well, that's the introduction to what our group is doing. Now, this is my today's plan. First, I will talk about an agent-based evacuation simulation, because tsunami is a big problem and a large number of death tolls are due to tsunamis. And here I will explain our model details and give some HPC enhancements we did. And around 45 minutes I will spend on hands-on so that you can do your own simulation and visualize the results. And there's a small change in the plan, and I'll take the 1:30 to half of the next lecture, 1:30 to 2:15, and in that one I will talk about our agent-based economic simulation. Okay, let's go into details. I think some of you already know what's agent-based modeling. It's a computational technique used for studying the behavior of complex systems arising from interaction of individual components, such as maybe the molecular dynamics is a good example. We know how a single atom of each type of elements, 92 elements, behave under different energies and different ionization. And if we write a software software agents which mimic each type of elements and put them together with the necessary or required initial condition, we can simulate what would happen. Just like that, in many other fields, these agent-based models are used in physics, social science, as an example. Spreading of contagious diseases, swarm forming by birds, or migration of animals, even pedestrians, traffic, and so on. And in these simulations, agents autonomously interact. We just give the rules, and they, according to their surrounding, they will autonomously decide what to do. And this provides a good natural description of the system. And with for our problem, both evacuation and economy, this is ideal tool because we can look at we can simulate considering the smallest possible entity in the real world. As an example, we can include every single evacuee or every single individual economic agent like firms or individual consumer. Due to their flexibility, we choose agent-based models. Well, why do we need large-scale simulation of evacuation? Well, I think a large number of you are coming from Indonesia, Malaysia, these countries, and I think no introduction is necessary. Okay, and in case of Japan, Japanese government is expecting a major earthquake in this part of the country, and in some coastal areas, they expect the tsunami wave to arrive within 10 to 20 minutes, and there are no high grounds around, and some of the most major part of the population in some cities are elderly. So evacuating these populated cities within 10-20 minutes is a major problem. And there are many softwares to do it. Actually, there are most of these softwares are simplified. They want to keep the model simple, at the same time reduce the computational time. But we think the simplified models are not sufficient. The conditions during an earthquake and a tsunami could be quite diverse. As an example, it could happen in the night, visibility is low, and it could be winter, and the earthquake which created the tsunami, generated the tsunami, could have rendered all the traffic lights not working. And we would like to use, let some people use cars, because elderly, we cannot expect elderly or the needy people to walk to the evacuation center. And also part of the roads may be blocked by the fallen debris due to earthquakes. So just using Q models or cellular models is not enough. We want more sophisticated models. This is what we are dealing with, human lives. So it's better to use the sophisticated model. So with this in mind, we develop a bit sophisticated model. Sophisticated means computation heavy. Computation heavy means we have to use high performance computing. And our model consists of two main parts. One is environment, other one is agent. And environment is pretty easy to explain. It's our surrounding. And so we model our major part of the environment as a grid. It's actually a matrix of ones and zeros, so some numbers. And according to what's happening, we update our environment. As an example, if a tsunami wave is propagating, according to simulations, we update the details of the, maybe we can do it every 5 seconds or every 30 seconds, whatever the frequency you need. And then accordingly, the agents around will take some action. And as you know, using grid is good for giving a high resolution model of our environment. However, in decision making, this is a bad one. If you want your agent to calculate a path to the nearest evacuation area, doing it a grid means it takes quite a lot of time. And also, these agents should be a little bit smart so that whatever they experience on the way to the evacuation area, they should store in their memory and reuse in their decision making. And if we refer these decisions to the grid, the amount of data we have to store in each agent is quite large. So in order to address this, we created a graph, which is just the walkable, the linkage of walkable spaces within this domain. And even though we update the grid, we don't update the graph. So this work as their ordinary day knowledge. And whenever agent encounters certain blocking or blockage of the roads, they store that information with reference to this graph, and they use that in their decision making. So by mixing these two, we could attain reduce the computation time. At the same time, we could implement flexible agents. Agents are simple. They consist of a series of certain functions, we can classify into three parts. See means perceiving what's around, and think means think what to do according to what they see around, and then put that into action. We have implemented number of functions with composing. Putting these together, we can compose different types of behavior, like as an example, resident or visitor or volunteer, or these types. This is a typical view of the simulation. This gray color background shows the grid. This line shows the graph. I overlaid it so that you can see it. And we have added nodes at least every 25 meters so that agents can store their experience in a sufficiently high resolution. And the blue colors are the pedestrian walking by the side of the road, and the black color long arrows are the vehicles on two lanes. Each agent scans their environment in high resolution. This circular radar-like pattern is this agent's visible boundary. And then analyzing it, it can see, okay, this road is open, this is open, this is open, there's no trouble, I can walk, and there are something blocking the way. And I can see this set of agents. It cannot see whatever outside this boundary. Each agent has its own length of visibility according to the age of its features. So we try to mimic real agents, real evacuees features. To see how we can mix the graph and the grid together, I created this toy problem. In this one, before the evacuation, the earthquake produced some debris, and accordingly I expanded the foot area of the building. And on the other case, there's no such debris and the path is clear. Right after the earthquake, somebody here doesn't have any idea what to expect on the way. So both plan the same road to the evacuation center. And it will walk, and once it come here, once it scan and figure out this part is blocked, it will store in the memory and recalculate the path, and then he will dynamically adjust his way to the evacuation center. Let's see what happens. So it comes here and see it, identify it's blocked, and once it comes here, it will automatically identify, and so on. It will dynamically adapt. If the water is there due to tsunami, it will again change. So this way we can make these agents dynamically respond to the changing environment. And other part is this: when we walk on the road, we try to avoid hitting on each other, and our walking speed changes according to the density of the people around and the narrowness of the road. We must reproduce this behavior too. And so we call this part collision avoidance. And what we do is, here I have this A and B shows the two agents. We approximated circular shape with the diameter equal to our shoulder width. And we move these agents to first transform it to the velocity space. I will not go into details. And then created this velocity object. Actually, that's all the velocities. If he set its velocity such that its arrow will land inside this object, they will definitely collide. So that's the main idea. Okay. So after creating this velocity object, it will adjust its current velocity so that it will not enter this area, and also the changes will be minimum. And that's so-called optimal reciprocal collision avoidance. We adapted this one. In case of, there are many, so we create so many for each neighbor, one velocity object, and then using integer programming, we find the minimum change that this agent should do to avoid collision entering these gray color areas. That way we avoid collision with the minimum changes to the agent's velocities. Well, and adapting this collision avoidance algorithm, we made the pedestrian to interact and pedestrian car in narrow roads, because Japan has so many narrow roads and vehicles, and you may have already seen vehicles and people walk on these roads interacting. And in case of a tsunami evacuation condition, there can be such heavy interaction. Also vehicle interaction. And next our question is, okay, now our agents can avoid collision. Can they reproduce the observed behavior in the real world? To test that, we did several tests. In one of the tests, we tried to reproduce a data set collected by Dr. Mori and Tsukaguchi. Actually, this data was collected somewhere in Kobe city. So according to that experiment, we set up this single direction flow and with different densities of agents, and observed random number of random agents, velocities, and their number of agents in their surrounding. And to validate the vehicle pedestrian interaction, we collected a set of data near Japanese temple near University of Tokyo during a festival season. And these are some of the photos data we collected. And these graphs shows our validation test. For the pedestrian, this dotted line shows the observed data by Mori and Tsukaguchi. And these whisker boxes shows our results. As you can see, they are in quite a good agreement up to 2.5 meters per every square meter, which is quite a high density. And in case of car, also this is the collected observed data, and these whisker boxes are our simulation results. And interestingly, for pedestrian car, the crosses are our simulation and dots are observation. Also, it shows they are in quite a good agreement. This shows, well, it's no longer a toy, or this is not a game, but we can reproduce the observed behavior. So our results have a certain reliability. And one of the question often discussed problem is, during an earthquake, tsunami evacuation, can we let some people use vehicles? And since this is an interesting problem, important problem, we introduce vehicles and try to make their behavior as close as to the real world. And junctions are places where the vehicles slow down and interact with people. We wanted to reproduce the trajectory of vehicles at a junction closely. So this is a set of collected data by a group of researchers at Kobe University. And by analyzing this one, we found that we can actually approximate this reasonably accurate using NURBS or B-splines. B-splines are easier to work with, so we use B-splines even though it has around 25 centimeter error, but 25 centimeter is not a big number compared to for our application. And then in a domain we want to simulate a very large domain, like several tens of kilometer by tens of kilometer, and there can be many junctions. So creating these trajectories manually is not possible, so we automated it, and these are some of the samples. This is a 2-lane. This is a 2-lane at a T-shaped junction, and this is Y-shaped, so on. And now we have trajectory. At the same time, we have to make sure that the vehicle speed along the trajectory also is accurately captured. And then by analyzing the data set collected by Professor Hideki at Kobe University, we found that we can approximate the speed of the car along a curved trajectory using this cubic equation. And here we compare our agents' speed at different location along the trajectory with the observations. These crosses our agents' speeds, and as you can see, they are in a reasonably good agreement. Also, we try to avoid collision with each other at this curved trajectory and make sure that their speeds are such that they can stop the car at the acceptable deceleration using also we made sure pedestrian cars also interact such that car will run at a speed so that they can stop the car before reaching the very close to the pedestrians on straight paths, at the same time on curved paths. This is a bit computationally demanding, but it was necessary. Now, next let me go to a demonstrative example. I don't plan to go into details because this is the same problem I will use for the hands-on, so that you can try it yourself and play with it. And so the problem is set such to evaluate how many cars we can accommodate without hindering the progress of the evacuation, because this is an important problem, as I discussed earlier. We created this hypothetical scenario for this simulation. We consider there's emergency evacuation after an earthquake, and it was in night around 11 p.m. And all are asked to evacuate to about 10 meter high ground. Here we, as an extreme case, we asked them to go to a high ground rather than entering a tall building. Also, we assume that traffic lights were rendered non-functional by the earthquake, and so there will be a vehicle interaction uncontrolled manner. And to reduce the congestion, we said the car users, if you are using a car, you should start evacuation before 15 minutes. Usually, right after evacuation warning, people don't start immediately evacuate. They take 10 minutes. And if you are going to use a car, you should evacuate before 15 minutes. This is just a strategy, we can change it. And for the study area, we use Kochi city, which is in the, and we set the evacuees start location according to the occupancy data of Kochi city. This is the center part of the city. And we consider 4 scenarios. In first scenario, all people were asked to walk. In the second one, 6% of the evacuees were allowed to use cars. We choose that 6% from the slowest, from the farthest from the evacuation area. And we increased that number to 9 and 15. So 6% means around 1,224 cars, and 15% means around 3,000 cars. And so this graph shows the average speed of pedestrians, and this is average starting time of evacuation. It's around after around 10-12 minutes. In case of cars, this is the average speed, and this is the evacuation start time. We moved the slowest portion to cars in different problem scenarios. This graph shows our results. This is the percentage of cars evacuated with respect to time. As we can see, when it's 5%, all the cars can reach their destination within 1 hour. And when we increase the car percentage, the number of cars that can reach the evacuation center is reducing drastically. That's because there's a congestion and people are also on the road, and that will the progress of cars will be reduced. And then we consider another 15% scenario where we restricted cars, tell the cars, you cannot take these roads if you are using a car. And as you can see, that increased the progress of the cars even with the 15% car use. So likewise, we can change the strategies, and instead of doing the experiment in real world, we can do this possible strategy search on the simulator and find out how efficient, how effective these are quantitatively. And when you look at the total number of people evacuated, we can see this blue line with 5%, we can accelerate the evacuation. The black line is the all walking. When it's all walking, not everybody can evacuate, but with cars, all can evacuate, reach the evacuation center. And 15% simply cars will reduce the number of evacuees quite drastically, but if we restrict the roads to certain roads to the cars, we can improve that performance and reach better performance. This I did manually, but instead if we automate it, I'm sure we can find much better strategies. This shows the routes selected by cars without any restriction with 15%. And when we block certain roads for cars, it's quite distributed all over the domain, and that's why it's giving us a better solution. In case of pedestrian, it's not much affected. Anyway, we will see this in your hands-on. Now, let me go to the HPC, because this is HPC school and we cannot, I shouldn't skip this part. Well, when it comes to the performance, we had to both focus on the serial and parallel. In case of serial, one of the heavy time-consuming tasks was this radar-like scanning. And we need high-resolution the scanning. If we do this scanning on a grid, it involves the non-consecutive access to non-consecutive memory areas. As you can see, if an agent is scanning this way, it's a consecutive memory segment 1, 2, 3. But when it starts scanning in this direction, you have to jump, and that really kills the performance. So to address that, what we did is we, instead of making each agent scan every time, we pre-computed which cells will be intersected, and considering 9 locations within a cell. So in this way we can avoid computation of these intersecting points on arbitrary direction, but now we have a pre-computed template. That reduces the computation time, but still the non-consecutive memory access was the main trouble. And to address that one, what we did is we created a certain hash table to minimize the memory access. As an example, if you look at these 2 rays, they pass through the same set of cells. So if you know this cell doesn't have anything blocking on the way, we know that the other one also doesn't have. And also we know up to the second cell, both this ray also has the same behavior. And using this information, we created a certain hash table. And so this is our original codes when we scan how many number of times we access each cell. As you can see, the center part is heavily accessed, but if we use this hash table, we can significantly cut down accessing the same cell again and again. And that really reduced the, improve the memory access performance and also the computational performance. So this is our original code. Each color shows the instruction commit. This is the L2 cache access, and this is a memory access. So path hashing significantly reduced the memory access. At the same time, the other instruction for data fetching. And then we use a sector memory that also contributed to the another half a second reduction. And then with certain refactoring, we could reduce the original 4 seconds to 1 second. That's actually 4 times, making it better. So this way we could reduce the computation time involved in the agent C function. And likewise, we did some other performance improvements to the other parts, serial performance improvement. And for for parallel computing, since we want to simulate hundreds of square kilometers and millions of agents, we needed parallel computing. For the parallel computing, as you learned in the first day, we decompose the domain and assign each domain to different computing nodes. And then to maintain the continuity of the entire domain, we copied a part of this blue region to the other partition, other computing nodes part, and then part of this red region to the part of this blue partitions domain. And we call these halo regions or ghost regions. And then at each time step, after each time step, once we update compute this agent state, we update the corresponding agents copy here. And once we update these blue agents on the partition boundary, we update corresponding agents there by sending their updated state. This way we keep the continuity of a domain. This is ghost update we call. The agents, like in most of the physics-based simulation, like molecular dynamics or finite element method, each point or each element has a fixed amount of data. It could be displacement, velocity, and pressure. But in case of agents, they involve quite a large amount of data, and some of these data are dynamically growing. As an example, what an agent experiences on the way to the evacuation center is dynamically growing. They have different lengths. So sending back and forth this information during the ghost update is quite challenging compared to the the normal physics-based simulation. I will skip the part of it. And then these agents move with time. And that movement, so initially we split the domain into pieces such that each part has a nearly same number of agents. But with time, these agents move, and after some time, now we can see this partition has a lesser number of agents, but this has a higher number of agents. And that means this finishes its task quickly, this CPU, and other is still doing computation. There's a load imbalance that wastes computational resources. As you learned in the first day or second day, we have to rebalance it. To do that, we do the repartitioning. But repartitioning is not an easy thing. Once you repartition, you have to redistribute these agents' information into the new partition. Since our data structures are complex, that also actually gave us quite a troublesome time. And okay, I will skip this one. And sometimes, with time, what happens is a number of agents, like these agents go to evacuation center, they disappear from the simulation. As you can see, number is decreasing. And when the number is decreased, we cannot use the original number of CPUs because if I start with 32, I don't have enough number of agents to simulate on 32. So we started remapping the agents to a smaller number of CPUs to keep the simulation running. Otherwise, it started aborting.